host user groups, so again, if you're interested in attending a user group, or if you have a user group you want to start, talk to me, okay? We'll talk to any improver. We host for free, we provide food and drinks for free, so just let me know, we'll get something set up. And we have a bunch of, this is just a partial list of some of the user groups we have. freecodecamp.net, I think they're not calling themselves Code for Y'all, user product community, so on. And if you're interested in any of them, let me know. I'll figure out when they're meeting and give you the info. Okay, let's see. Next up, we also are hiring, so if you're looking for a role or you know someone who's looking for a role, reach out to me. Here's some of what we're open for. Okay. And again, we've got some workshops. In this case, we've got Kafka. So if you're interested in Kafka, again, let me know. And there's a QR code, our schedule, and again, we do more training, including like Scrum, Scrum certification. So once again, if you're interested, let me know. And with that said, that concludes our intro portion. And now, some preliminaries here. Get straight into where's your gutter? There. Sometimes scroll. Okay. Okay. So just a real quick reminder for those of you who are new. Okay. So our group is called GEM, or Just Enough Math. Okay. And basically, my name is Ahmed. I'm a programmer here, and this is.
I'm Justin. I'm a math teacher.
Okay. And professor.
I wouldn't go that far. I'm somewhere in between. Yeah, that's true.
Well, you teach at a college, so you know that's
I teach community college.
Yeah.
And so yeah, so we regularly meet to talk about math tools that aid in software development, whether it's in the development, planning, analysis phase. And our goal here really is to present just enough math to identify problems, patterns, and either how to solve them, or at least give you enough of the lingo to know where to look next, because you kind of get an idea of what kind of problem you're dealing with. All of our talks are available as Colab notebooks, right? And they're basically just cloud-hosted Jupyter notebooks with content and executable code. Anyone who wants, I can provide them the link of this notebook so you can play around with this on your own. Okay, they're accessible to all, so let me know. And these talks tend to be more, again, collaborative, so definitely chime in if we say anything that doesn't match with your experience, or you want to add something. We're not experts. I mean, obviously, I'm a programmer, he's a mathematician, but we get into a lot of areas where we either dabbled in some things or even picked up some extra stuff to kind of present, okay? So definitely feel free to chime in.
Hey, one point about the Colab notebooks is that if we share, you're able to fork your own copy over, so you just save a copy, and then you can just sort of do whatever you want with it.
Right.
So obviously we're not all going to be editing the same document.
Yeah.
So just pull your own copy, and then you can just have at it.
Yeah. So as long as you have a Gmail account, which is free, and a lot of people have them.
Yeah.
You can play around with the examples and experiment yourself.
Yeah. Just under File, save a copy. You're good to go.
And just let us know. I'll provide the link. I'll probably post it in our LinkedIn group. And for those who haven't joined the LinkedIn group or are interested, you can just take a picture of this QR code. I'll take you to LinkedIn. We also have it at the bottom of the presentation. And yeah, join the group. I'll add you in, and there we announce future meetings, links to Colab notebooks, maybe any kind of follow-ups, comments. But we do meet the first Wednesday of every month. So, okay, cool. Yeah, and so with that intro out of the way, Justin can get us started on optimization.
All right, the topic of the day. No. Okay. Yeah, so this is a bit of a follow-up from our last GEM meeting, where we covered optimization, mathematical optimization, a very specific subset of that, which is what's called linear programming, where you're in this world where everything is linear and optimization is easy. And there are a lot of well-developed algorithms and mathematical methods to solve. Just a quick aside.
Remind me what optimization is.
thanks. Yeah, so just to remind everybody, when we talk about optimization here, when we say mathematical optimization, that has a specific meaning. That's a certain class of mathematical problems, right? It's not about optimizing your code or any other sense of the word optimization. So optimizing code is, of course, it's about making your code run faster, stuff, and things like that. So, but hopefully, if you're able to frame a particular problem as an optimization, a mathematical optimization problem, you might incidentally make your code run faster. It's possible, but this is not about making your code. This is not about making your code run faster. It's about studying mathematical optimization
And doing less work.
and doing less work. Yeah. So yeah, in keeping with our philosophy, we try to show you, give you sort of just enough math jargon and methodology to kind of make a difference, possibly in your day-to-day life as a software developer. Hopefully give you some tools to work with, so you can look at problems in a certain way and be able to interpret, documentation of identify useful packages and interpret their documentation effectively. Because a lot of packages, especially with optimization, they're written. The starting point is, from the mathematical perspective, they write their code kind of in that way. So you have to kind of understand what a mathematical optimization problem is in order to sort of give it to the package and say, hey, can you solve this for me? Speaking of which, we are profiling a package, right? So we're talking about...
Yes, we're using Pymo. It's spelled P-Y-O-M-O. I'm pronouncing it Pymo because I don't know how to pronounce it. I was too lazy to look it up. So especially Pymo, it's a free Python package for optimization. It's quite powerful, and it's apparently used by quite a few heavyweight organizations. So last time we did Google OR tools, but we decided to do Pymo this time since Pymo has nonlinear optimization and better ways of doing it, and it's quite easy to use. Lots of good documentation out there.
If you were attending last time, we covered OR tools. FYI, we discovered later that OR tools only does linear programming. So, just so you know, I mean, it's fine for that. But if you step out of linear programming, then there are no tools there for you. So that was another thing that prompted our shift to Pymo. Again, it's spelled P-Y-O-M-O.
Yes. And I'm pronouncing it Pymo, so move on.
No one said, am I going to pronounce it Pyomo?
No, Pymo.
All right. Pymo then. All right. Yeah, the old dilemma of naming software packages and pronouncing them. What's the name? I don't know. All right. Anything else? Preliminary stuff? All right. So that's the package we're going to use. Ahmed especially is going to use that package to solve an optimization problem that comes out of some work inspired by a case study he did in a prior, or a task that he accomplished in a prior role. So try to stay somewhat grounded in realistic problems, things that you might be faced with yourself. Okay, so what is an optimization problem? First up, all right. If you're here last time, this is just old news, but for new folks, so if you're trying to make a decision, right, about how to set certain quantities in your whatever situation you're managing, right? You may have in your mind, a certain number of quantities that you can control, and then you may also have an objective that you want to achieve, right? So if all these things are quantifiable, right, you may come up with a model where you can say, well, here are all the things that I can control, right? These are quantitative values. I can set them. And then I can come up with if I can come up with some sort of a model that tells me how those quantities impact the quantity that I'm trying to do something with. I'm trying to either maximize it or minimize it, right? Think profit or risk or cost or something like that. then I can write down an optimization problem formally, a mathematical optimization problem. So I have to, first of all, be able to identify these variables, what they are, and then somehow model how they feed into impact my profit or whatever the quantity is that I'm interested in maximizing or minimizing. So here's some examples are bulleted here. So as a store manager, maybe you can decide the inventory that you keep on hand. This is something quantitative. I got this many tubes of toothpaste, I got this many toothbrushes, and whatever else, right? These are things that I can decide, right? So how does that impact the space that's in my storage room, for example, right? How do these, I have a fixed space that I can keep things in. Say I want to minimize, minimize or maximize this or the space taken up in the storage room, just depending on what you want to accomplish. Do you want to keep more space available, or do you want to make sure that you're using all the space available, something like that, right? So maybe a better example actually is like a money-based example, right? So if you have a stock portfolio and you have a certain amount of money that you want to allocate to among various stocks, right? That's the decision that you can make. How much do I invest in this stock? How much do I invest in that stock, and this stock, and that stock, in order to maximize my return, right? So somehow you have to model, that return, that expected return, for any given allocation, and then you want to find the allocation that maximizes that, right? Based on your model. In summary, you're faced with an optimization problem if your objective is to either maximize or minimize some quantity, for example, profit, cost, or risk, and you have known variables that exist and can be controlled by you, right? And those variables impact that quantity that you want to optimize, right? So you want to find the right configuration of values for those decision variables. We call them decision variables, by the way. So that brings us to all the terminology that we're going to use, or at least most of it. So a decision variable is one of those variables that you can control, right? You can make a decision about, right? And it impacts the value that you want to optimize. See, the objective is in fact the quantity that you want to optimize. Again, I'm using the term, by the way, optimize to be as a catch-all term for either maximize or minimize. So depending on what you want to do, right? So the objective is the quantity that you want to optimize. The objective function, and sometimes we use objective and objective function interchangeably, but it is a mathematical function that is a model, right? It describes mathematically how the decision variables feed into they're put into a function, and that function produces the resulting value of the objective, right? For example, I feed a certain allocation into my model about the stock portfolio, right? And the objective function will return the expected return on that, that corresponds to that particular allocation that you fed, right? So let's see, what else? Feasible domain. The feasible domain is a collection of ways that you can configure the decision variables, right? The feasible values that you can assign to your decision variables, right? These things, not every value can be assigned to every decision variable in every instance, right? Some variables, some represent quantities that don't make any sense as negative numbers, right? Like think, the amount of money that you invest in the stock portfolio, something like that. Are you going to invest negative money? Well, not in the typical scenario, right? If you're just looking at, you've got a pile of money that you want to allocate, you're saying, okay, how much am I going to put here? How much am I going to put here? The minimum amount that you would put onto a stock that you would invest in a given stock is 0, right? You would just simply choose not to invest in that stock, right? So, just as an example. So, the feasible domain could be determined by things like your budget constraints, like, again, the stock portfolio example. obviously you have a certain amount of money, right? And you can't invest more than that, so that is a constraint on your decision variables, right? So those type of constraints play into the definition of your feasible domain. Okay. The optimal solution is the ultimate decision that your optimization problem, if you solve it well, produces for you. It tells you how to do these allocations in your stock portfolio, right? So that's what we call the optimal solution. It's the configuration of the decision variables that give us either the maximization of the objective that we want, or either the maximization or the minimization of the objective that we're looking for. All right, so far so good?
Any questions?
Good to go? All right, so here's some terms from basically from math class. All right, you have a global maximum or minimum of a function. That's the largest value that the function achieves. All right, so the function in this case, in this context, we're thinking of it as the objective function. So it's in the case of maximizing profit, we're talking about the maximum possible profit, right? Or if we're talking about minimizing cost, we're talking about the minimum possible cost, right? As you know, that your objective function can output, right? All right, and that's of course what we're looking for, part of the feasible or the optimal solution. Well, okay. So a local, so that's different from a global maximum or minimum. We have what's called a local maximum or minimum, which is just a local phenomenon. So if you're looking at your function, if you're lucky enough to have a function that you can graph, which is generally not the case, but just for the sake of visualization, if you're looking at a graph, it could have a local sort of a hump here, which is sort of a local maximum, right? So if you kind of zoom in on just part of your function, you might see that there's a maximum value there, but like way over here, there's another maximum, right? That's much higher than that local phenomenon, right? So this can be to put it mildly, a cause of great difficulty in optimization. Sort of local minima or maxima are sort of the bane of the whole field of optimization, right? So you don't want to, because your algorithms get stuck on them and stuff like that. Anyway, so we'll leave that for later. But just so you know, that's a very important thing to be aware of. All right, so so the terms optimum, optima, etc. are used generically to talk about either maximum or minimum, and the plurals are maximum, minima, and optima. Just so you know. All right, so examples. So we good so far? Anyone want to ask anything? All right. Examples, maximizing profit. All right, so this is something that everybody can at least concretely imagine or recognize the importance of, right? So, if you're running an enterprise, especially a big enterprise, you want to have some sort of a model for how you can impact your profit, right? How you can make more profit. So in this is sort of a toy example that can come out of a basic calculus class, all right? So if you have a factory that has a certain capacity, right? It can produce 1,000 of some item in a given time frame, right? And I'm going to use the generic item widgets, right? So due to supply and demand issues, all right, profit is not maximized by maximizing your production. So maximizing out your production at 1,000 widgets is not the optimal solution, typically, right? Because you have supply and demand. Once you produce past a certain point, profit might start dipping down, all right? So a little bit of an extra terminology here. The number of widgets that you produce is called the production level, so I might use that in a bit. And this is our decision variable, and we'll call it X. All right, so X is the production level, and that just means the number of widgets that are produced by this graph. All right, so we'll analyze two profit models, and they're plotted using, since it's a function of one variable, they're easy to plot, and we'll plot using Desmos you're getting Desmos a little plug here. It's a free online graphing calculator if you're not familiar with it. Right? It's absolutely, hands down, the most amazing graphing utility on the internet. I use it all the time in class. No one should ever have to buy a graphing calculator. All right, so we're going to use Desmos to plot these things. And P of X is going to be basically our profit model, right? The profit that results from your choice to produce X widgets. So okay, again, X is our decision variable, P of X is our objective. Or technically, P is our objective. Profit. Okay, so we're going to consider widgets that have two different natures. The first one will be that the widgets are produced and sold individually, and this is what we might call a discrete situation. And the second situation is where it can be, sort of infinitely subdivided. I can sell half a widget, or a third of a widget, or a quarter of a widget, or any fraction of a widget. Think something, like sand or something that you could sell, in any amount that you want, not just individually. All right, so in example 1, we have sort of a nice objective. All right, it very clearly has a maximum. Right, so here, this is our profit model using the widget. How do we find the optimal solution here? Well, just sort of move over here until we get to where it looks like I'm at the top of the hill here, right? So it looks like our maximal profit is somewhere in the region of $48,000, right? And that's 460 widgets. Maybe I can play with it a little bit more to see, to make it go a little bit higher, right?
Those 460 widgets are decision variable?
Yeah.
Okay.
That's the value that we can assign to the decision variable X to get the maximum profit.
So what happens is that your optimization package is going to give you 470. After you feed it the problem, it's going to say, produce 470 widgets. Mm-hmm. That's going to be your highest value. And then it's going to tell you you can make $48,084
Right. So in this visualization, again, the decision variable, or the feasible domain sort of lives on the x-axis here, right? So that's where all the options for your decision variable are, right? By the way, what is the feasible region here in scenario 1, where widgets are produced individually? Any comments?
You can't make negative widgets, so.
True. So you have your classic we insist that it's not negative. We're not making any negative widgets. True. So in scenario 1 in particular, though, what about it? What impacts your feasible region? They have to be integers, right? They have to be integers. And this may seem like not such a big deal, but it can be a big deal depending on the problem.
Yeah, and we call these discretes.
Yeah. Yeah. Technically, discrete could be like any discrete set. It doesn't have to be integers. You'd have to maybe do some rescaling or something to make it, make it an integer problem in that case, or there'd be some trick to do it. But yeah, so in this case, yeah, if the widgets are produced and sold individually, you can only sell an integer number of them, right? So only integers are part of your feasible region. Right? And what about the other case? Where the widget can be subdivided as many times as you want. It can be basically anything. Any fraction of a widget is possible. What would be your feasible domain then?
Your real numbers greater than 0.
Real numbers greater than 0 and less than or equal to. So remember the capacity of the factory.
Oh.
Right? The capacity of the factory is 1,000, right? So yeah, everything from 0 to 1,000, right? Right. So there will be different answers depending on what your feasible domain is. So this says about 470 or let's see, what is 469? 460. I'm not able to get 469. If I zoom in, I get an extra 5 cents if I make 469 versus 470. So it looks like 469 is my optimal solution. Okay. All right, but so this is the type of problem where these little differences aren't big. They don't hugely impact your profit, right? I could have done 469, 470, it doesn't matter. And by the same token, if I were to treat this as a continuous problem where I'm talking, I can make fractions of a widget. Again, that would not impact the answer much in this problem. So we don't actually have a problem on hand to illustrate when that issue can make a difference. But if you look at the Colab notebook from the last gem, you'll see one. So we had the bus problem, then we had the paint can problem, and you can see that in those instances, actually, if you don't treat them as an integer problem, then you're going to get results that could be either non-optimal or even outside of your feasible region. So you have to be careful about whether you're treating it as a continuous problem or an integer problem, and that is indications directed for the solver. So there are integer solvers in PyMo and in OR tools, and then there are continuous solvers. So you have to choose the correct solver when you're doing your coding. So here's our less than nice objective. What do you want to do with this? What do you think? What should I do? Move this to find the derivative?
Yeah.
Actually, the expression for this is a little bit ridiculous. This is a totally made up profit model, but if you look at the profit model, here it is. I've got x to the power 1.1 times the natural log of 3x times the sine function. Right? You want to take a derivative of that? Maybe with a Simone package or something. It can be done, for sure. Huh? Yeah. So, okay, so if you take the derivative, what are you going to find? Okay, so
that's where the math comes in.
That's where the what?
That's where the math comes in.
That's where math comes in. So if you're solving this in calculus class, that's what you would do, right? And you might find this point here, right? You might find this, right? Right. So that's a maximum. This is a maximum right here. You must say, okay, that's my optimal profit right around there. Except for what? Psych. That's your whole function, right? So I know I went back to the 80s and 90s for psych. I know. I'm sorry. So that means I got you. So okay, this is what your profit model actually looks like. You can tell we have a local maximum here, right? Which, if you're not careful, your algorithm can just get stuck there, okay? And you'll miss this global maximum profit. So I purposely made this so that the global max was much bigger than the local max, right? So you're missing out. The point is that if this is your profit model, you're missing out on a ton of profit. And if you're not, and this is a case where, okay, you might say, hey, I'll just go and plot it on Desmos, but that doesn't work, right? That only works here because this is a function of one variable, right? How many businesses do you know have one variable in them, right? A very idealized situation, okay? So generally speaking, there will be many variables, and you can't visualize a function. You can't do it. There's no way to do it. So you're basically flying blind. Okay? All you have is an optimization routine. Or calculus, perhaps. You might be able to do calculus to solve for a global maximum. But that's pretty tough math, honestly. So you might be just reliant on an optimization routine. And optimization routine, it's not like it's visualizing what's going on. It can't detect the structure of the function. Okay? Not the function as a whole. It can detect the structure locally of the function and use that local information to try to get to a maximum. But again, this is a local maximum, right? So that's why your algorithms may converge on that local maximum instead of the global. And in fact, PyMo fails us in this respect. And this is our code for running PyMo on, on this particular function, and it returns 181 as a solution, right? Which does correspond to this local minimum. I'm sorry, this local maximum. So the algorithm missed the global maximum in this case. So, and this is a simple case. Yeah.
When you say that if you're not careful, your algorithm is stuck on a local minimum or a local maximum. Are you guys going to go into detail about what you mean by be careful, or what that means in practical terms?
No, because unfortunately, we're unfortunately we won't get to that topic. What we chose to focus on instead is the situation where that is not an issue. Okay, so basically what you have is this big field called optimization, right? Mathematical optimization, which contains all sorts of these optimization problems that are nonlinear in nature, and you might have these local optima to deal with, right? But there are subsets of that are much more tractable. So, for example, linear programming, which is what we talked about in the last GEM meeting, right? In this GEM meeting, we're going to talk about convex programming, which is nonlinear but still tractable. There's still solid algorithms that will converge, no question.
So, and just to add to that, so the idea is that if you do, if you understand the structure of your problem and understand that you may have, multiple local, like for example, maximum or minima, what you could do is, one, you could have it solve the problem, right? It gives you a maximum, and then say, I know there's probably multiple maximum in here. Feed it back in as a constraint to give me something higher and see if it spits out something higher. Maybe go a few times and try to get a good solution. So I was trying to find the perfect solution. May not be tractable, but you at least know you can grind a few times.
Yeah.
Second possibility, and this is actually something Jared had brought up, we talked about, is there may be some algorithms that might be capable of doing a better job on them, like we were talking about simulated annealing. If you know you're dealing with a package that may have some of these algorithms, you might say, hey, I know the structure of this problem, I've got multiple optimization points. Let me go ahead and make sure it's using a solver that at least can do that and try to get us a better solution. And a lot of times you oftentimes get a solution that's good enough, but not the best solution just because the problem space could be so big, it's gonna take you forever. So you're like, okay, this looks pretty good, we're just gonna kind of roll with it. But at least you know not to necessarily take the first answer or to look for other algorithms. So that's ways you could at least try to deal with the problem. There may not be a perfect way around. Does that help you a little bit?
Yeah.
Yeah. So there was the what is it called?
Simulated
annealing. Another one we talked about was genetic algorithms. I don't really know what that is exactly. But so those are the two big things that came up in our discussion. Those are still out there, to try to handle, nonlinear problems that might have multiple local optima. So, okay. All right. So, yeah, feasible domains. So just a quick key takeaways on this. Feasible domains can be discrete and continuous. And when multiple local optima are involved, then the algorithms can be blinded to the global optima. All right, so we talked a bit already about constraints. So I think we have a pretty good feel about what they are. So they're conditions on the decision variables that limit, what they can be, right? They may not be able to go past a certain point or less than a certain point, etc. Now, how do we describe these things mathematically is another thing. Okay, so I've written down several examples of constraints, and in three types. The first type we'll talk about is inequality constraints. They can be simple, as in up here, x is greater than or equal to 0. That's your classic. It even has its own name. It's called a non-negativity constraint. Comes up a lot because a lot of quantities simply are not by nature negative, right? You can have other constraints, simple constraints like x less than or equal to 1,000, then more complicated constraints. These next two constraints that you see are linear inequality constraints. How do you know something's linear? Right? You see an expression, how do you know it's linear? Right? There's more? What do you mean more than one?
The exponent is 1.
That's right, the exponent is 1. Yeah, so every exponent that you see is 1, even though it's slightly ironic that I say that you see it because it's not, you don't actually see it, right? It's understood to be right there, right? So what's the exponent on this variable here, right? It's 1, right, even though we don't write it. If, by contrast, what's the exponent on this x1 down here? Right, the exponent on this variable is what? 2, right? So this is a nonlinear expression. Keep down here, and this is a linear expression.
And to be a little bit more broad about it, so one, you're not going to see an exponent linear expression. You also won't see things like log, exp, or like max functions or absolute values because they'll alter your expression not linear.
So, it's funny you say that because this one is actually linear.
Huh?
The one that has log in it is actually linear.
Like I've been called bull, but let's
It does. So yeah, you have to be a little bit careful with that, right? So just because you see a log there doesn't mean that it's not linear. It could be. It might be transformable into something that's linear in which case. So that's why you have to be a little bit careful. But anyhow, so we won't get into that. Just exponentiate both sides here. Okay. So that's equivalent to x2 is greater than 1.
So I'm interested, if you put a log though in a solver, will it treat it as a linear solver?
Well, if you put that constraint, so if you start with a linear solver and then you give it that
And
constraint.
you give it a log, yeah.
You have to pre-transform.
Yeah, yeah, in my world it's not linear.
It would probably complain if
So it's not linear. Remember, just enough math, we're trying to use packages, right?
All right, so let's not go down this rabbit hole. Okay, moving on. So general form of such constraints just look like this, where G is just any function that you can think of. So G is some function of the decision variables. We write that's less than or equal to 0, and that's a general form of a constraint. Okay, so you may question that there's a 0 there. Well, think about any of these. How could I transform these to make it fit into that form? Well, for just say the top one, x1 squared plus x2 squared plus 10 equal to 9, right? Just subtract the 9 of them, right? Now you've got a function of the decision variables on the left-hand side. You've got less than or equal to 0, right? So sometimes I think maybe the software packages might insist on that format, but I don't know that for sure. What do you say? No?
Insist on what format? Sorry.
Having your constraint in this, having 0 on one side of your constraint.
It depends on the package. So like Pymo Google OR tools is actually quite flexible, but like I think was it the Scikit or SciPy learning actually does want the constraints in that form. It's a fairly low level package.
Okay.
So it depends on the package, but some of them do actually make that assumption. Some of it even take the problem in the matrix form, in which case that assumption is kind of forced that.
Yeah.
Or that form.
Quick math question. What if I want to switch the direction of the inequality sign?
-1, right?
Multiply by -1. There we go. So if you multiply this one in particular here by -1, then I'll have some function of the decision variables on the left-hand side, and then less than or equal to -1, and then I would add 1 to both sides to get the 0 there. So this is a general form. This form here is a general form. Because any inequality constraints that you could think of could be written that way. Right, with a little bit of what we call finagling. All right, so another type of constraint you can have is equality constraints. So I'm not going to go. I think I'm going to skip this bit in the interest of time. But again, there's the general form here, right? Some function of your decision variable is equal to 0. Okay, so it has an equal sign instead of an inequality sign, right? This is less common, and the most common use for it is that actually, if you have that kind of constraint, you can eliminate one of your variables, right? Because if they're all equal to 0, then you can just solve for one, and then then its value can be inferred from the values of the others. So it's really an extraneous variable, right? So there's an example of that here, right? But I won't bother. We don't need to go through these details. But that's the idea. It's basically, you reduce your problem by dimension if you have an equality constraint. Okay. Okay. Integer constraints. Really, we already talked about that, right? So some values only make sense as integer values. And again, we have a strong warning here that this is very relevant to your choice of solver. Okay. So if you have an integer problem where the fact that the values are intrinsically integer could conceivably impact your problem, you need to be careful. So there is some consideration about that. It may be that it's not such a big deal. And my sense of it is that if you're in a situation where it's you've got you have the factory, you have the factory where you can produce 1,000 widgets. That's quite a lot of integers, right? Like there's, if the function if your profit function is sufficiently smooth, it's not going to be like jumping up and down between integer values. So what we call a continuous approximation to that problem is going to be sufficient, right? You can just solve the continuous problem, round off the answer, and be done with it. But when when the values tend to be a little bit lower, as in the paint can problem, right? Where you might be talking about 3 cans of this type, or two cans of that type. These are smaller values. There's the feasible domain is just a very small set. Then being off by an integer can make a huge difference. So sorry I don't have that example prepared today, but it is in the Colab notebook from the previous session. All right. So writing your problems down, this section of the talk really is just about kind of how to format an optimization problem. You need 3 elements. Every optimization problem needs at least 3 elements, at least from a mathematical point of view. You need to know whether you're talking about a maximization or a minimization, sometimes called the sense of the problem. You need a concrete formula for the objective function, and you need a full description of the feasible region as a list of constraints, if there are constraints. Right? There's a such thing as problems that don't have any constraints, called unconstrained optimization. Okay, but if there are constraints, it's called constrained optimization, and you have to list the constraints when you're stating the problem, if you happen to be planning to write a math textbook. Also, if you happen to be trying to feed it to a solver, you need to, generally the solver is going to need all these 3 things in one form or another. Okay, so I wrote down a couple examples. Ahmed was criticizing my visualizations, so I just want to know I want to know what everybody thinks of my visualizations of these problems. Okay. So here's one of the problems. All right, it looks like this. I wrote a bunch of code to visualize it, and this is what it looks like. Okay. So if you look back, sorry, I'm jumping around too much here. So if you look back, what we have is it's a linear objective function, right? Basically, I've tacked on the square root of 2 to make the graph look nice, so you can basically disregard the square root of 2. But then I have this constraint here. It's an inequality constraint. Anybody remember what that looks like from your college algebra class or algebra in high school or whatever? So it's a circle, right? So it's a disk. It's all filled in.
Hit run all. Reconnect it and do run all. Make sure it's going to run all. Well, just make sure we decide to run the example, because there's stuff that it installs in the environment. Yeah. And then you keep talking through it, but it's going to install stuff. Yeah.
All right. So the feasible region is going to be a disk or a circle with radius 1. A circle, with the interior filled in, and it's going to have radius 1 because of the 1 there on the right-hand side of the block. All right. So let's take a look at what that looks like. course, we can't see it just yet. So,
Yeah,
all right. While we wait,
probably
we'll
just
just,
let's install
let's
it
just-
without time.
okay, we're just, okay, there it goes. There. All right, so in orange down here, this is the feasible region. All right, so this is a three-dimensional figure, right? So the blue is the surface that is produced by the objective function. So the objective function was linear, if you remember, and linear functions produce graphs that are planes. Okay, so this blue is a plane, right? It's tilted off to one side. And down here in this horizontal this horizontal plane, right? You can think of this as the x1, x2 plane on the bottom, right? That's where the feasible region lives, and that's a circle, as was commented, right? So the objective function is here, kind of, the graph is sort of hovering above the feasible region. And this little tiny red dot down here, that represents our optimal solution, right? Because that's the lowest point on the surface, right? That is still above the feasible region. In this case, it happens to be right on the edge of the feasible region, right? Okay. So, next example, just run through really quick. This is a nonlinear objective. Again, we have a circle or a disk for a feasible region, except that because of these inequality constraints, it's just going to be a quarter disk. Okay? So let's take a look what that looks like. And it's a maximization problem. Okay.
Oh, that's this. I didn't know that.
Well, down below, yeah.
Oh, that was this.
Down below is the quarter disk. So the feasible region is down below, horizontally, right? It's this orange region, right? It's this quarter disk. And then the graph of the objective function is up here. It's a nice bowl shape, okay? All right, and then it was a maximization problem, so we're looking at the top of the hill here for our solution, right? Okay, so we won't take a whole lot of those visualizations. Just a quick idea of what these things can be visualized as if you're lucky enough to be able to visualize them, right? Again, there's only two variables here, right? How realistic is that? Well, it might be realistic sometimes, but most of the time it's not. All right, so this is the main thing that we want to talk about today. Convex programming is a subset of optimization, which is, generally speaking, is nonlinear. You can be dealing with nonlinear objective functions and nonlinear feasible regions, right? So the feasible region can be something other than like a polygon, right? It can be something like a circle, like we saw up above. And the objective functions can be nonlinear, but they are generally, they have this kind of nice bowl shape, okay? So we'll get into examples of that in just a second. Why do we care about this? It's because these problems are extremely tractable. They have good algorithms written for them, and they do occur commonly in applications. Okay, so just to get a handle on what this means to be in the world of convex programming, let's look at some simple examples of convex functions. So here's a convex function that we're all familiar with. It's a parabola, right? So notice the nice bowl shape, right? Here's another one. This is, by the way, lines are technically convex. They meet the criteria for being convex, although they're a little bit boring. So here's another. Hold on, I meant to here. Let me skip that. And talk about the next one. Oh, I see. Zoomed way out. Okay, so here's another example of a convex function. Notice that it doesn't have to necessarily be a bowl, but in this case, it's kind of like a half of a bowl. This is also convex. Here's another one. And these all have different formulas. They could be found in your calculus or college algebra text. So here's another one. Another one looks vaguely parabolic, although its formula is not that of a parabola, but similar. Here's like a little snippet of a cosine function, the part that's convex, right? All right, so that's the idea. So of course this has an analogy in higher dimensions as well, right? So we already saw an example of kind of an upside down bowl shape. That's in the realm of convex programming. Speaking of which, that example was called, it was actually an example of a concave function, right? So if you have the upside down bowl or half bowl, that's called a concave function. And these are literally the same concept, because all you do to convert a concave function into a convex function is to multiply it by -1. That just flips it upside down. So anything that any statement about convex functions applies also to concave functions in a slightly appropriately restated. Okay. So speaking of statements, let me sort of scroll back up here. I just want to take a moment to make sure to read this to you. So, if you, by the way, there's a book I linked in the bibliography called Convex Optimization. It's linked down in the sheet in the bibliography. And you can find this excerpt in there on page 138. It says the fundamental property of convex optimization problems is that any locally optimal point is also globally optimal. So translation, if you have found a local minimum, okay, they're using the term optimal here, but really they're talking about minimum because the optimal means minimum in pure math text, usually. So what they're really talking about is minimum. So if you have found a local minimum, then it is in fact the global minimum, right? So in other words, once you find a local minimum, problem solved. And that's why convex optimization is so important. It's so in such a well-developed and nice field. Okay. So algorithms cannot get stuck on local minima because there aren't any. Okay, except for the global one. Okay. On the other hand, one bit of bad news is that you're not guaranteed to have local minima. So they're not guaranteed to exist. But because again, think of like sort of the half bowl shape. Like it might be technically convex, right? It comes down and kind of runs this way and just kind of keeps going down forever and ever. So it has no minimum. So it's not guaranteed to exist. But if you find one, that's the answer. Yeah.
In those, because you guys are talking about constrained optimization, right?
Right.
You're going to have a minimum. It just might be the constraint.
It has to be constrained in such a way that the feasible region is bounded. Because you can have feasible regions that that have constraints, but they're not. It's not a bounded region. Okay, it might just go off in one direction forever and not stop. It might have a cutoff here, but it goes off in this direction and never stops. Right. So if it's a bounded region, and you're talking about inequality constraints where the inequality is less than or equal to, and not just less than. That's another important thing. So that's what we end up with, a closed bounded region, then you're guaranteed to have an optimal point. And that's true not just for convex functions, for general nonlinear functions as well. If it's general nonlinear continuous functions. So anyway, that's another result from optimization theory outside of convex optimization. All right, so we ran through that bit. So that's your introduction to convex optimization, what it is basically, and why it's awesome. I think with that, we'll just let Ahmed take over. Okay.
I'm gonna skip the derivation because we have 8 minutes left.
Okay, sure.
So, okay, just show the formula. Yeah, just show the formula. Skim over all the details. Okay. So let's get down to practical applications. So previous role I did a while ago was with market research, okay, media math. And I was with a company that wrote and produced data for basically figuring out who listened to what radio stations, or who watched what TV, or who visited what websites, that sort of thing. And so you had advertisers and advertising agencies who would actually buy or subscribe to this software and this data. and basically use it to try to apply to things like advertising campaigns. Okay? And one particular tool that they used was something called reach and frequency. I'm just going to talk about the reach point. And this was a tool that let you know, hey, if I buy, so many spots on so many different media, how many people can I reach totally? Okay? And they would use that to decide how they're going to allocate their advertising budgets. So at the time, at the time we did this, this was a manual application. People actually had this thing that basically looked like a spreadsheet. They put in different numbers of ads, and they would keep on playing around with the numbers until they saw values they liked. And when they got something where they're like, yeah, it looks good enough, they kind of went ahead and actually planned their advertising campaigns around that. Thing is, this reach was actually something where if you did it manually, you would probably not get the best solution. You probably wouldn't reach the most people. And in reality, behind the scenes, it's actually a nonlinear constraint optimization problem. We didn't do it as such, but I'm going to walk you through how we could have made the user interface simpler and made the results better by actually using what we know about nonlinear constraint optimization.
And it was convex.
Yeah, and it was convex. I mean, at the time, I never really, again, I feed it into the solver. If it gives me an answer, I'm good enough, right? All the other stuff is that's why I have solvers, right? So I have to do the math. But a little bit of the math knowledge does help. So everyone kind of familiar roughly with what we're trying to do with this application? Okay. So, okay. So if you had something like this, right? Like you had an idea of hey, I'm trying to reach the most people. I've got 10 different media, I'm trying to reach the most people. My budget is say, I don't know, let's assume it's 1950 and you only need $10,000 to actually advertise, right? So your decision variables, remember that's the output of your optimization optimization problem, is a number of ads you're going to put on every media. That's your decision variables. You want to know how many ads do I want to put in every one of the media that I have a choice in order to maximize my total reach, maximize the people I reach. Your constraints, I have a budget, $10,000, $1 million, whatever. Stay within it. And then your decision domains. Obviously, you can't put less than 0 ads. The most number of ads you can put are however much are available for sale on the media in question, right? One media may not have sold out. They may have 50 spots, another may only have 5, right? So each one of your decision variables could have a different domain. Do you think the decision variables are integers or reals? I want to know how many ads I'm going to buy. Integer or real? Integers, right? Yeah. Okay? So this is basically a discrete nonlinear optimization problem.
Convex.
Yeah, whatever. That's why I have solvers, so I have to think about these things. So
You have two dips and some comments?
yeah, multi-dips, remember? Multiple dips.
One dip and some comments.
Yeah, they're two diffs, non-convex. Yeah. I should have showed some examples of non-convex.
You already did?
No.
Yeah, your multiple minimum. Remember, it wasn't
Oh,
convex.
right, yeah.
Pretty sure.
Yeah, the second profit model, yeah.
Yeah, the
That's
whole
not
local
convex.
minimum that was in
Yeah.
convex. Yeah. Okay, so what makes this nonlinear? Why is the reach nonlinear? So let me ask you a question. Let's say you've got an ad, okay? And your ad's gonna reach a certain number of people. Let's call it X. And you go to this one medium and you're like, hey, I'm gonna put 3 ads on here. And let's go ahead and say X is 10%. Let's say that ad's gonna reach 10% of the people. If you put 3 ads, are you gonna reach 30% of the people? Yes or no?
I doubt it.
Your gut tells you no. You doubt it? Okay, why? Of course it's a follow-up question. Why?
Because you can saturate your audience.
You can saturate your audience, good, but even if you don't saturate your audience, why? Let's say you don't saturate. Do you think you'll still reach 30%? Let's say your saturation point is 50%. 3 ads, each reaching 10%, your saturation point is 50%. Will you reach 30% of the people?
What vision is the question?
Sure. You have an ad, and every ad can reach 10% of the people on a medium. Your saturation point, the media's rating, okay, is 50%. Okay, so you're not going to saturate.
So the maximum you can possibly reach with this ad is 50% of the population.
Well, the maximum you reach with enough ads, right? Yeah, it's 50% of this, yeah.
On this
of-
medium.
Yeah.
Yeah.
No, because you have overlap. You might have overlap. The people, you have YouTube and Reddit, but the person might be same. This is the same person reading YouTube.
Or you can on the same medium, right? You put in 3 ads, right? First ad, 10% of people get reached. Okay? Ad number 2, some of the people who see it may have seen it before anyway. So you're probably going to reach less than 10% with your second ad, right? Third time you put it in there, some people may have seen it the first time or the second time. You're probably going to reach even less, right?
Yeah.
So essentially what you have is a case of diminishing returns almost from the get-go.
What you care about is new eyeballs, not just eyeballs.
Yes,
Yeah.
new eyeballs. Yeah, absolutely. And that's reach. Now, repeated eyeballs is something they do care about. That's the frequency part, and that's a whole other thing. Because they care about how many times people see an ad and maybe remember, or just get sick of your ad and don't buy, right? It's true. They'll actually try to like vary between, say, 3 to 10, and after 10 they figure they're probably going to come at you with pitchforks and torches because they're sick of your ad.
Head on, apply directly to the
Get that jingle out of my head.
Yeah. And they call it negative response or whatever. But yeah.
And so that could be another constraint on the problem.
Yeah.
So if you start involving frequency, then that's, okay, in addition to your budget constraint, you might have a constraint on frequency.
Yeah.
You might set, you want a minimum frequency or maximum frequency.
Or both. Yeah. Exactly. We could expand the problem to include frequency. Yes. But for new eyeballs only, right? So it's always diminishing returns, right? And this is key because it's diminishing returns. The problem becomes nonlinear, right? So like, for example, an example of like a reach curve, and let's make a growth rate a little less steep, right? Let's say 10 is our growth rate, okay? So essentially, you're always getting diminishing returns. Your first ad, okay, you're gonna get your 10, but after that, it's, less and less and less and less, until you hit your saturation point, where the line basically asymptotes. That's our rating. In this case, I have our media's rating as 50%, right? Every ad reaches 10%, but of course, every subsequent ad's gonna get less than 10%. And because this is not a straight line now, you can see the line has a constantly changing slope, it's nonlinear. That's another way of thinking of nonlinearity. If I plot this function, assuming I can, does my line have a constant slope? Or does it look like a curve or some disjoint abomination, right? Nonlinear. Cool so far?
Did you show the formula?
Huh? Oh, the formula's right here. So, so we got the formula right here. Now this formula is actually derived basically from like a growth pattern, and don't really have the time to get into details because we're running late already. But essentially, this is essentially like the growth formula that we're using right here. Okay? So essentially, we're just taking a rating and we're multiplying it by 1 minus, and then we have e raised to the minus growth rate times the number of ads. But that gives you your asymptotic curve.
Yeah, it's basically 1 minus an exponentially decaying term, which gives you this saturation pattern.
Yeah. And the more steep your growth rate, of course, the faster you hit saturation. Okay? Alright, now, a few caveats, okay? This is a bit of a simplified model, but in reality, what we actually built wasn't much more complicated than this. Reach and frequency is a whole controversial area. I mean, you want to talk about controversy in media math, talk about reach and frequency. It seems like 50% of the people hate it and the other 50% don't trust it. But people pay money for it, right? Yeah, I mean, people pay money for it. They'll grumble, but they're going to say, where's my reach and frequency?
They don't know what else to do, right?
Yeah.
That's the thing. If you don't know what else to do, you just keep doing the same old thing.
Yeah. And so even though there's a lot to be said about the accuracy of this, they pay money, so we make it, right? And so this was very much an ad hoc model, and we would basically build the curves based on what we knew about the media and like kind of points in which they feel it should pass through, right? And different companies have their own models. There are a lot of different reach and frequency models out there. Some of them, you'll even see their curves a little bit exponential at some point before it starts turning, get into diminishing growth. And again, a lot of it is like very rule of thumb or what looks right, okay? So a lot of this is very ad hoc. But we do have at least a formulation for it. So the parameters really here are, well, what's your growth rate? The rating we measure, the growth rate's really kind of something you sort of negotiate, figure out. and that tells you how fast you hit saturation. So, with multiple media, right? And this is where the optimization problem becomes interesting. You're not just trying to buy on one medium. You're trying to buy on multiple media, right? And these multiple media have different reach curves. You can see here that WXYZ has our highest rating, but has like the slowest growth, right? You can see how long it takes to get there. ABC, of course, has the lowest rating, but man, it gets there fast. And of course, QRS is somewhere in the middle. And this makes the problem pretty interesting because it's like, well, what kind of blend do you have to buy to maximize your reach, knowing that your highest medium is always going to get you there fastest. Plus, each one of them has different inventory constraints, right? Now, this too is simplified because I'm not accounting for overlap between media, right? In reality, there's going to be some audience that's going to overlap, and so there should be an additional overlap we subtract based on the folks who are buying and how many spots we have. But right now, I'm just going to assume that these media are fully independent. A very unrealistic, idealistic assumption. But it keeps at least this example understandable. Okay? So now I'm like, these are my media, these are my choices. What do I need to do? How can I figure out what the best blend is given the budget? Okay? So far, so good? Okay. So when we get into this, so here's a code, and let's actually talk a little bit about the PyMo code because we kind of like glossed over it before. So here I just highlighted to find a reach maximization function. And this chunk right here basically just slices out the data I need from the dictionary and pass it in, right? Nothing really to do with PyMo. Here's where the PyMo stuff starts, right? Line 7. So if I'm trying to build something in PyMo, I declare an instance of a model using concrete model. This next guy right here says, hey, I want to start getting some decision variables, but I want them as an array, because I don't want to sit there and declare a decision variable each time. I may want to have 10,000 decision variables. So this lets me declare arrays of decision variables, right? In this case, my first index is 0, and the last index is whatever my growth rates are, okay? The number of adds is where I'm going to start putting in my constraints, okay? Actually, I'm sorry, the number of adds is my decision variable, sorry about that. var declares a decision variable. This tells me, again, it's an array, which I set up here, and this tells me what the domain of my decision variables are, right? Non-negative integers. This is a discrete problem. Now I give it the objective function, right? So I just say, hey, again, I declare an objective function with objective, and I give the expression for the objective function. And here I'm summing up the reach across all of the adds. Again, I'm assuming independence to make this example simpler, okay? And of course, I got my growth rates and my ratings, right? And I'm saying, hey, maximize this expression, maximize the sum of all of the reaches across all the media, given each one's growth rates and ratings, okay? And in this case, I tell it to maximize right here. That's where we use the term sense, and PyMo takes that. Now I want to start giving it my constraints. I have my budget constraint, right? I say, hey, here's my constraint, and again, for my constraint, I give it an expression. In this case, the dot product, the weighted sum of the number of adds and the cost for each medium has to fall within my budget, right? And again, PyMo's high level, so I don't have to worry about, inverting the inequality or anything like that. But other packages at a lower level might have you do that. I also have a constraint on my inventory. I can't have more spots than the medium is willing to sell. So here I say, hey, give me another set of constraints. Remember, I'm using this to declare arrays for my inventory, and every inventory for every medium, okay, the constraint is that the number of adds is less than or equal to available inventory for that medium. Then I just go ahead and call a solver factor. Okay, and I just say, hey, go ahead and solve this model, okay, and its default just keeps it from spitting out a lot of output. And then I just go ahead and spit out the results, right? After it solves it, and here normally I should be checking to make sure it actually finds a solution. I know it will, so I left it out, but in reality, you want to also check and see, hey, did I find an optimal solution? Did I find a feasible solution? Or did I basically find no solution, right? So I know that this has a solution, I'm leaving this alone, but again, normally put something in here. And then I'm just printing out the results, right? So I'm iterating through all of my array elements here. I already have my media names. The number of adds which I declared that are decision variables. When I use that value, it retrieves the value assigned for each one of them. So this is the number of adds I need to buy on every medium. and then a model that reach actually gives me the total reach achieved, which is the value of the objective function, or the objective value. So far, so good?
What kind of algorithm is used to solve this?
So in this case, I'm actually passing in. So in this case, I'm actually passing in the solver I want to use here, and you'll see I'm going to use them two different kinds of solver. One of them is IPOPT, which is actually a continuous one, and then there's bond-min, which is actually discrete. Now, what they're using under the hood, that's a good question, but they've got the documentation on what's being used if you go to the Pino site. Yeah. And I'm doing that just so you can see some of the fun that happens when you try to use a continuous solver on a discrete problem. But yeah, good question. And there's actually a lot more solvers with Pimo, and you can actually install more solvers, so you've got a pretty wide array of solvers. And then I go ahead and just plot the reach data just so we can again have the curves for references. So I run
Which
this.
solver did you use on the profit model?
You mean for?
That one variable profit model with the local maximum? Which,
I
did you
believe
use the integer solver or the continuous solver?
I believe I used the bond min. We can go back and see because that was an integer problem, right? Or was it continuous? If it was continuous, I used IPOPT.
I guess you treat it as continuous. So you
No,
use
it
this
would probably been
IPOPT.
IPOPT. Yeah, I popped. Yeah,
I popped.
I popped.
And it failed.
Yeah.
I don't remember. It failed. So,
Well, I found the local minimum, wherever that's worth. But yeah. So for example, if I run this and I say, hey, maximize the reach, right? And here I have a set of two media, right? And I've got their cost, their growth rate, inventory, and I give it a budget of just like say $30, again, super cheap media. And I say, hey, IPOP, use this. IPOP is a continuous solver. It says, okay, we need 3.29 ads on WABC and 13.52. Now, of course, you can only buy an integral number of ads, right? But this is important because I want you to just think about this for a moment. Sometimes the intuition is, oh, well, let me just round these, and I need 3 and 14. But rounding doesn't always work. And this may not be the example that shows it. So IPOP is a continuous solver. I think bond-min is the... So bond-min in this case gives you 3 and 15, right? IPOP previously, and bond-min, remember, is a discrete solver, right? So 315 versus IPOP, which is 3, round this up 14. So you can see here that the rounding doesn't work. If you take a continuous problem, if you take an integer problem, a discrete problem, you run it through a continuous solver, and you think you could round it, you're going to be a little bit off. And that's because it can distribute the results differently. So you always want to make sure that you use the appropriate solver. In this case, bond-min is a discrete nonlinear solver. Okay? So very important. And you can see here, you can kind of like, and this is one actually, was this the one that we actually worked out analytically and confirmed that the results match,
Yeah.
right? Yeah. So Justin did the whole work with pen and paper or chalk, whatever it is mathematicians use, and confirmed that these results were not fun.
it took 5 pages, but I write really big, so.
Unplugged.
Yeah, the unplugged, exactly.
The unplugged.
Computed unplugged, right. Yeah. And this is another case where we just kind of, ran through solutions just to kind of show how, again, you gotta hit some edge cases with your budgets, right? In this case, we had a discrete was bond-min. We see here if your budget's $99, it'll tell you you need to buy 3 on the first 2 media, nothing on the fourth one. But if you switch your solver again to the continuous, you can see here, it's like, here in this case, it's like, hey, 3.9 and 2.9, so that's 4 and 3. Which if you round them, it's not even a feasible solution because you go over budget.
Yeah, if you round that to 4 and 3, then yeah, you
4
bust,
and 3,
you bust
yeah.
your budget in that case.
Yeah.
So,
4 and 3, right? Your cost, yeah. So 4 and 3
Do not
actually causes
treat
bust, yeah.
an integer problem as a continuous problem, unless you're totally sure that it's no big deal.
Right. So that's going to be key, right? It's like always know. And this is like where the importance of knowing if you're dealing with a discrete problem or a continuous problem, because the solver you're going to use will be impacted by that. The same holds if you're solving a linear problem. We talked about that last time. Linear versus non-linear. Again, your solver. Pimo supports a large number of solvers. So the basics you just need to know are discrete, continuous, linear, non-linear. You know enough to know what solver you need. Give it that solver, you should be okay. But avoid the temptation to round. Okay? so yeah, so pretty much just kind of wraps up the case study on how, on at least how we can apply nonlinear, like nonlinear programming, and a case study of where it actually gets used and how Pymo can do it. Now again, Pymo's got a ton of features. There's a lot of documentation on this. I think the government produced like a 300-page document on using Pymo because I guess
Yeah, it's
government-
been going on for a long time, and
Yeah.
it's been used by the government agencies
Yeah.
and stuff.
even the government said don't do it.
Documented. It's,
Yeah.
should be totally legit.
Yeah.
thing.
Yeah, if you read the documentation basically says, yeah, we told everyone not to use it, but everyone's using it, so here's the documentation. It's a little bit smarmy, actually. But, so this pretty much wraps up this portion of it. Any questions on anything?
Just go back up.
Sure.
I want to get the code.
Sure. Oh yeah, so you want to look at the Pymo code?
No, I just want to see something.
Sure.
It's all, I popped.
Yeah. And IPOP is available in a few other packages too, like Julia. I used IPOP for the linear regression example in Julia. That's a software I use for it was a quadratic problem, yeah.
Another convex problem.
Yeah. It was great, it was like a 4-line linear regression because it was done as an optimization problem.
Can I see just show the curves one more time?
The curves?
Yeah.
Sure. Well, let's see, are you good, Kai? Okay. So the curves like here?
So I just want to just show that they just make a comment. This is clearly, I mean, these curves are what? Not convex, but we would call them what? Upside down convex, which means what? Which is what? What's the word for that?
Okay.
So concave, right? So this is within the, you know, since for us concave means convex, right? So in math we don't really talk about, you know, because they're really the same thing. It's just one is just upside down. That's how we look at it. So immediately what you would do, like a solver would do, would just multiply each of those by -1, and then so flip them upside down, right? So now and then just minimize. So everything is typically treated as a minimization problem. So that's just how you know you're in the convex programming regime, and that's how you know that your solution is totally fine. Like whatever your solution that you get from IPOP is totally fine. Unlike the non-convex problem that in one variable for the profit model, right? In that case, you got a solution, and yeah, it was like, you know, it's worth something. It did find a local maximum, and you're making some profit there, but it missed the local maximum where you could have made a lot more profit. So,
Ahmed, you said you were solving this problem in a prior role, right?
Right.
How did that end up? What was the epilogue on that?
Well, the prior role was not done via constraint optimization. The prior role was literally, hey, here's all of your media. Go ahead and put in your ads and play around with it until you like what you see, which is kind of like the default. Yeah, most of the reach and frequency there was basically people were exploring and plunking stuff in, and again, people paid for it, they were happy with it. So this is like exploring that problem and how it would have been better. Because this is one of those cases of like, man, if I had to do this all over again and I knew about constraint optimization, I would have definitely been like, hey, you know what? You didn't have to enter in any spots. Just, these are the media, list whatever media you want, or leave it alone, and it's going to tell you exactly what you need to do if you give me what your budget is. As opposed to, let's put all the stuff in here, let me look at it, and after a few hours of playing around with it, hope I have a good enough solution. This would have simplified the interface and pretty much given them better solutions. Yeah, so this is like one of those, like, this would have been a better way to approach it had I known then what I know now. Yeah. And it would have been interesting to see how folks would have liked it, because it would have basically been a reach and frequency solver. And we could have gotten rid of the whole spreadsheet interface because you only needed to know what your budget was at that point. Yeah.
So do you know, does anything like that exist? Like, someone has implemented this already by now.
God, I hope so.
Okay.
Because this isn't rocket science, right? I mean, this is fairly straightforward, and if no one's implemented this really, really saddens me about the state of market research, because this is kind of an obvious thing,
Yeah, I was able to just derive it for using differential equations just in a few minutes. And then also I came up with an alternative derivation. So I came up with 2 derivations of this model. And it's just in a day or so. Now,
Yeah.
I'm sure this is out there somewhere. It may be considered, very old news at this point.
Yeah,
At least in academic circles, maybe academic market research, stuff like that. But how much of that actually sees implementation in the real world, I don't know.
yeah.
See, mathematicians are putting market research analysts out of work. is what you're saying.
I don't think so. That's the funny thing.
Yeah, it's different.
I mean,
Because if you read if you read like the papers on reach and frequency and actually like skim through a thesis, which is like a 400-page thesis
Yeah.
paper, there's like a lot of different models and no one's happy with any of them.
Yeah.
So there's like the ad hoc model, there's the accumulation models, and there's a whole list of statistical models that get into things like what is it, like the binomial, like a binomial distribution, and but every time there's like all these weaknesses and all these complaints. But I mean, every one of them is subject to the same thing. You can go ahead and formulate that, whatever model you have as an optimization problem. And again, just pretty much say, hey, here you go. So, like I said, I do hope that they did do that because this isn't terribly unique. I mean, it's, that's a great thing about optimization. It's like, it solves a very intuitive problem. So it shouldn't be rocket science. It's, I want to maximize my reach. Yeah, I got a budget constraint. Yeah, I got inventory constraints. At this point in time, anyone off the street can basically do this with a package. So yeah. So your answer is I hope, but no market research. It would sadden but not surprise me if no one did this.
a lot of times there's huge disconnect between, what's going on in research
Yeah.
versus, what's being implemented.
Yeah.
Just like kind of silos of communication, it's not happening. It's also hard to communicate with people who are not in your field. I have trouble communicating with Ahmed, and I've been friends with him for a year. Because we have very different perspectives on problems,
Well, I'm a pragmatist, so I'm very pragmatic, and I'm like, well, I just want to solve the problem, and you can go play with your equations. Let me just solve my problem. So we kind of squabble over this.
And I would have problems. I worked with biologists in graduate school. I went to math graduate school. I worked with biologists. Again, same issue. It's like it's hard to communicate. We're looking at things differently, and so that part of this meeting, this group, is to kind of try to bridge the gap a little bit to see, because there are things to do there in the middle of fields. There are things to do that can be helpful, but it's a little bit. There's kind of a barrier there. There's kind of like an initial startup cost going in that direction. So we're just trying to maybe make that startup cost a little bit cheaper for you.
Because a lot of the issues are also going to be just awareness of the tools, right? This isn't a hard tool, it's an intuitive tool, but a lot of people aren't really aware of mathematical optimization or even the fact that so many problems can be phrased in that it's solved with a package. So if you're not even aware that such a thing exists, it may not even occur to you. And even if you don't know the package exists, but you know the field exists, hey, let me look up algorithms, it's a thing. So a lot of this may even be stuff that you have very talented developers who don't even know there's such a thing, who don't even do it because they even think about it. And that's kind of like the whole thing behind this group is like, these tools are out there, these concepts are out there, you can bypass a lot of work, but you have to know they exist. And I mean, so that's kind of the thing,
Enough to use it, right?
Yeah.
But that's not as much as you might think it is. You just want to learn just enough, so you don't mishandle the tool, but.
And fun fact also, when Justin was talking about his derivation, he was deriving reach and frequency basically by working out equations. I just basically took a Python symbolic package, right? Fed the same process in there and then spat out the factorization. I'm like, hey, here it is. So we approached it entirely different. I just used software to also do that for me.
Symbolic. Yeah, that was interesting. You have to take a look at that.
Yeah, play around with Simpy. It's pretty fun too. It'll do all of this stuff and factor stuff for you too. But that's neither here nor there. Any questions about anything we talked about? Okay. So I'm going to make it a point. We're going to make it a point to post the link to this collab on the Google group. But email me if you.
Google group?
Not Google.
LinkedIn.
LinkedIn group. LinkedIn group. Thank you. But if you don't have access to LinkedIn, just email me. I'll send you a link directly. Okay. So you can play around with all these examples, mess around with them, experiment with them. And always, if you have any questions, feel free to reach out to either of us. Again, we got the LinkedIn group. Email me, right? We'll more than happy to talk about this or even assist. And again, we can get you the links to the previous sessions where we talked about linear optimization too. I mean, I can give you the collab links to everything we talked about from day one. Just let me know.
I need to make a repository of links, I think. Put it
Um,
in one place.
Well, I have them all bookmarked, which is kind of a very kind of, ad hoc repository, but
Yeah.
And again, for those of you who are interested, so here's a QR code. If you scan it, that'll get you to the LinkedIn Just Enough Math group. Feel free to join. Again, we'll post about any upcoming sessions and the topics, but as always, first Wednesday of the month, roughly around this time, same formats. And yeah. Okay. And no final questions. If not, I guess that wraps it up. We could break up into groups and squabble, or just chat away, or go home, or whatever the heck you want. But this, yeah, thank you very much for coming. Really appreciate it.